For a long time, Pluto was regarded as a unique object and was formally classified as a separate and valid planet in our solar system. But recent debates concerning Pluto's status, spearheaded by renowned astrophysicists Neil deGrasse Tyson and Michio Kaku, have rekindled interest in the planet and prompted more research into its place in the universe. These scientists have raised the possibility that Pluto and Neptune are headed for collision, which has raised many questions about how such a huge event could happen. What effects might it have on the planets and the solar system as a whole? Does this idea have a more complex and comprehensive explanation, or are we seeing a rare and unique cosmic occurrence? Let's examine the potential implications of a Pluto-Neptune collision. Even though Pluto was once thought to be a smaller, farther off object in the solar system, scientists are still quite interested in it. Key studies by top specialists indicate that Pluto's orbit is extremely near to Neptune's, raising concerns among astrophysicists like Tyson and Kaku about the potential for a catastrophic collision between the two planets. Whether such an occurrence actually threatens Earth is now the main question. First of all, how could this have occurred? One of the most peculiar orbits in our solar system is that of Pluto. Pluto has yet to complete a single orbit since its discovery in 1930, since it takes an astounding 248 years to complete one full round around the Sun. Its orbit isn't the only characteristic that sets it apart, though. It's also far longer than the other planets' more circular orbits. Pluto's orbit is also one of the most inclined orbits seen, with a 17-degree tilt with respect to the solar system plane. Pluto's voyage through space is made more challenging by its steep tilt and elongated shape. The way that Pluto's orbit interacts with that of Neptune is one of its most intriguing features. Contrary to what one may anticipate in terms of planetary location, Pluto actually approaches the Sun more often than Neptune for about 20 years throughout each orbit. And crucial question is brought up by this: why haven't Pluto and Neptune collided yet? The gravitational forces operating within the solar system hold the key to the solution. Astronomers were baffled by Pluto's orbit as soon as it was discovered. Pluto's orbit is inclined and elliptical, which makes it a subject of great research in contrast to the other planets in the solar system, which follow comparatively flat, aligned routes. Because of the gravitational interaction that keeps the two orbits stable, the fact that Pluto's orbit crosses Neptune's does not always mean that the two will collide. Known as the three-body problem, this balance demonstrates how the Sun, Neptune, and Pluto interact through their gravitational pulls, such as forecasting future locations based on their current motions and forces acting on one another. This phenomena demonstrates how the gravitational attraction of the Sun, Neptune, and Pluto prevents the two objects from ever colliding. The mechanism known as libration, which makes sure that Pluto crosses Neptune's orbit at least 90 degrees distant from Neptune, and that the two bodies are never at the same place in their orbits at the same time, is responsible for maintaining this steady relationship, according to astronomers. Furthermore, Pluto's orbit demonstrates degree libration, which is a shifting or oscillating pattern around its trajectory. This method lowers the collision risk even more. The gravitational wobble effect, often referred to as VZK wobbling, is another significant component of Pluto's orbital stability. It describes how the gravitational force of the Sun, Neptune, and Pluto interacts to keep Pluto in orbit despite its apparently unpredictable trajectory. Understanding how planetary orbits change requires an understanding of the three-body problem and these factors that control celestial motions. In addition to providing insight on Pluto, these interactions advance our understanding of the solar system as a whole. Although the stabilizing forces kept Pluto's orbit stable, numerical models carried out in the 1980s showed that even little adjustments to the planet's initial conditions may make it more unstable over extended periods of time. Pluto's orbit has stayed largely stable over millennia in spite of these possible anomalies. The stabilizing effects of planets like Jupiter, Saturn, and Neptune on Pluto's trajectory have also been emphasized by recent models. For instance, Neptune and Pluto have a resonant orbit, which means that Neptune completes 3 orbits for every 2 that Pluto completes. The stability of Pluto's orbit depends on this resonance. Neptune is not the only planet, though, that affects Pluto's orbit. The gravitational pull of Jupiter is also important, and it has even been demonstrated that Saturn aids in stabilizing Pluto's orbit. According to these models, Pluto's orbit might be sustained for billions of years, if not forever, by Jupiter's gravity alone. Therefore, Neptune, Jupiter, and Saturn must work together to keep Pluto on its current path. Our solar system would be more chaotic without these stabilizing factors, and planets like Pluto would collide with one another or be thrown from their orbits completely. By examining these interactions, we can better comprehend Pluto's orbit and gain important knowledge about the universe's overall dynamics. In light of this information, predictions of a possible collision with Neptune make Pluto's orbit much more fascinating. Pluto's complicated orbit serves as an example of how our solar system is dynamic and how forces operating on one item can have an effect on the system as a whole. It also serves as a reminder that these complex dynamics can bring even seemingly chaotic orbits into a balanced state. This equilibrium is mostly due to the orbital resonance principle, which explains how Pluto's position and velocity may remain stable over time despite its erratic trajectory. The way Pluto's orbit interacts with that of other celestial planets, such as Neptune, has been better understood thanks to programs that simulate these orbital mechanics. Modest changes to the model's parameters can demonstrate how Pluto's orbit could be drastically changed by even small shifts in its position or speed. Pluto's orbit can still be erratic even with stabilizing elements like degree libration and asymmetry libration. Large changes in Pluto's long-term trajectory could result from little changes in its beginning conditions. Pluto's orbit, however, is extraordinarily constant over billions of years, suggesting an underlying structure to its travel around the Sun despite its seeming unpredictability. For astronomers who have to take into consideration the dynamic character of planetary orbits, this unpredictability poses a difficulty, even when it appears chaotic. Numerical simulations show the limitations of our theories, but they are also a great tool for forecasting celestial behavior. Because these simulations mostly depend on the correctness of their beginning conditions, even the slightest mistake could have a significant impact on the outcomes, making accurate forecasts challenging. Pluto's unpredictable orbit serves as a reminder of the universe's ever-changing nature. Even though scientists have learned a great deal about space, Pluto's erratic trajectory shows how much more is yet unknown. By examining the gravitational pull of massive planets like Jupiter, Saturn, and Neptune on Pluto, scientists can learn crucial information about the dynamics of the solar system as a whole. It shows how the stability of other objects in the system can be significantly impacted by the locations and movements of particular planets. Prominent astrophysicists have voiced concerns about a potential collision between Pluto and Neptune despite these stabilizing factors. Using Pluto as an example, renowned astrophysicist Neil deGrasse Tyson provides a distinctive viewpoint on the secrets of our solar system. Tyson highlights the significance of continuously improving our knowledge of celestial mechanics. Tyson was involved in the process of reclassifying Pluto from a planet to a dwarf planet. Tyson contends that as our understanding of the solar system expands, Pluto's reclassification was a necessary correction rather than a loss. He sees the peculiar orbit of Pluto and its relationships with Neptune as evidence of the fundamental unpredictability of space. Tyson warns that while Pluto's orbit is now stable, it may undergo major changes in the future. This option emphasizes the extent of our current understanding of the forces forming the solar system and their wider ramifications. Tyson's viewpoint highlights space's unpredictability and serves as a reminder of the intricacies of celestial mechanics. His examination of Pluto's orbit in respect to Neptune highlights the unexpected nature of even well-studied planetary movements. Tyson says that even while things seem stable, they could change over time because of dynamic forces in the solar system, which are still mostly unknown. Although it caused widespread controversy, Pluto's reclassification as a dwarf planet is in line with our expanding understanding of the solar system. According to Tyson, as our knowledge and resources for space exploration advance, this change was required to better our classification scheme for celestial objects. Pluto continues to be a significant topic for scientific research even if it is no longer regarded as a complete planet. Beyond Pluto's classification, this growing knowledge adds to larger conversations concerning the stability of our solar system and the factors influencing planetary motions. Tyson's and other scientists' research is shedding light on the intricate workings of celestial mechanics. The implications of these Pluto-related debates for our comprehension of the cosmos are extensive. Another important player in the discussion of Pluto and Neptune, Michio Kaku, offers more information regarding the dynamics and possible dangers involved. Building on Tyson's findings, he investigates how minor changes in Pluto's orbit could affect the stability of other celestial bodies or result in a collision with Neptune. As our knowledge of far-off solar system objects increases, Kaku's contributions help us comprehend how we could anticipate and potentially reduce these threats. Scientists use sophisticated models and simulations that monitor the gravitational pull between Pluto and Neptune over time to better comprehend the likelihood of a collision. The intricate relationships between the orbits of Pluto and Neptune, as well as the impact of other planets like Jupiter and Saturn, are taken into consideration in these models. Understanding Pluto's future and improving our capacity to forecast the actions of other solar system objects depend on this research. There is still uncertainty over the future of Pluto and Neptune's orbits, despite the fact that their connection is now somewhat steady. Over eons of time, the complex gravitational dance that maintains the two planets on their current trajectories may alter. Their orbits could be shifted by even the slightest change in their starting conditions, which could result in a collision or other disruptive incident. This uncertainty highlights the gaps in our present understanding and the difficulties in determining the solar system's long-term evolution. Knowing the factors influencing Pluto's orbit is only one piece of a much bigger jigsaw, but it offers important insights into how our solar system functions more broadly. The delicate balance required to maintain planetary orbits, not only for these two objects, but for the entire solar system, is best shown by the interaction between Pluto and Neptune. Therefore, studying Pluto's orbit is essential to learning more about how the solar system maintains equilibrium and how celestial entities interact with one another. Studying Pluto and other distant planets is becoming more and more crucial as we continue our space exploration. Despite their distance, these objects contain important hints that may help us comprehend the beginnings and prospects of our solar system. Scientists are gaining a better understanding of the forces influencing our cosmic environment by investigating Pluto's peculiar orbit and possible interactions with Neptune. These findings might have wider ramifications for research on other far-off objects, such as exoplanets and stars in far-off galaxies. The necessity of ongoing education in astrophysics is further underscored by ongoing studies on Pluto and Neptune. Future scientists will need to be adaptable and receptive to new ideas, just as Tyson and Kaku have modified their opinions in light of new research. Since the universe is always evolving, so too must our knowledge of it. There will probably be additional surprises regarding planetary orbits and the forces governing them as technology develops and human exploration becomes more thorough. In conclusion, the possibility of a collision between Pluto and Neptune is still a fascinating and complicated subject that fascinates both the general public and experts. This topic is very interesting because of Pluto's distinct orbital characteristics and the intricate gravitational dynamics at work. Although Pluto's orbit is now stable, the potential for future adjustments serves as a reminder of how unpredictable space may be. We learn more about the mechanics of our cosmic neighborhood as we continue to study Pluto, Neptune, and other solar system objects. This knowledge not only improves our comprehension of the past and present, but also influences our future predictions, which helps us better understand the vast and dynamic universe we live in. Understanding the interaction between Pluto and Neptune provides important information about the solar system's makeup. Astronomers can improve models of how far-off objects interact with one another in the wide expanse of space by better understanding their orbital dynamics. Scientists can better comprehend the forces governing the motion of planets, moons, and smaller objects across the universe and make predictions about possible future occurrences by regularly monitoring these interactions. These developments in space exploration aim to provide more general ideas that apply to a variety of astronomical bodies, rather than merely providing answers to particular queries. An illustration of how concentrated investigations into certain celestial objects might result in important revelations about the cosmos as a whole is the study of Pluto and its orbit. We might discover even more intricate behaviors in objects that we previously believed were too small or too far away to be of interest as our techniques for seeing space advance. The continuous argument over Pluto's classification underscores how our knowledge of space is constantly changing. In addition to the scientific interest in the orbits of Pluto and Neptune, what we know now might be quite different tomorrow as we collect more data and create better technology. This ongoing expansion of astronomical knowledge is exemplified by the quest to comprehend Pluto's place in the solar system. The possibility of a collision between Pluto and Neptune further emphasizes how dynamic and interdependent the solar system is. The gravitational pull between planets shows how intricate their movements are, even though this occurrence could appear far off or implausible. A single planet's orbital modification, for example, can trigger a series of alterations that reverberate across the solar system. This interdependence serves as a reminder that space is a dynamic system that is always changing and evolving, surprising us in new ways. Furthermore, the accuracy and equilibrium of the solar system are demonstrated by the possibility that a collision between Pluto and Neptune might be avoided over billions of years by minute gravitational forces. These events demonstrate that there is an underlying order and stability guiding the motion of the planets, despite the fact that many people may view space as chaotic and unpredictable. In addition to broadening our understanding of planetary orbits, this knowledge has demonstrated how these mechanisms have probably influenced the evolution of our solar system and may continue to do so. Undoubtedly, the ongoing findings will push the limits of our comprehension as we continue to investigate Pluto and Neptune. To learn more about the inner workings of the universe, scientists keep improving their models and running simulations to forecast the behavior of far-off objects. Every new discovery, no matter how minor, advances our understanding of the cosmic forces governing our solar system and beyond. Essentially, even though it is unlikely, the possibility of a collision between Pluto and Neptune is a powerful reminder of the extraordinary intricacy of our solar system. It reflects how scientific understanding is always changing with fresh observations and is a testimony to the never-ending pursuit of knowledge. Much though we may never fully understand these far-off planets and their interactions, every new finding advances our understanding of space and opens the door for future generations to delve much farther into the cosmos.